So we've been talking about conic sections, how we get those shapes by slicing a cone and the different shapes we can get. We've looked at ellipses, we've looked at circles, and now we're going to jump in and look at hyperbolas. So let's just go through the definition of a hyperbola. This definition is not going to really help us graph, but it's good that you are familiar with it. So a hyperbola is a set of all points in a plane, the difference whose distances from two fixed points, which are called the foci, is constant. Okay, so we have two fixed points called the foci, and if we look at that distance minus the distance of another point on the graph, then that is a constant number. So looking at the shapes of our hyperbola below, they kind of look like parabolas that are going away from each other, but they're not really parabolas, but they kind of look like it. Notice that we have two parabola shapes that going to the left and the right. We have two parabola shapes that either are going up and down. So in order to know which way that this is going, we want to look at our equation and we want to look at the piece that's positive. So notice for that first equation, we have x minus h quantity squared over a squared. Notice the minus is not in front of the quantity squared that has the x. So if that is positive, I know that it's going to be going, parabola shapes are going to be going towards my x-axis. Where if it was my y value that is positive, notice the shape, it's going to go towards the positive and negative y-axis. So that's how you're going to determine which direction. So for ellipse, it had to deal with the biggest number underneath or in the denominator. For hyperbolas, it deals with which one is positive when it's in standard form. So our center is actually not a point on our hyperbola, but it's going to help us graph things on our hyperbola. So just like with a circle and with the ellipse, it's in the form of x minus h quantity squared, and we have that y minus k quantity squared in there. So our center is always at hk. Again, h is always going to be with the x value, and the k is always with a y value. Opposite sign. So in here, we have two axes. For the ellipse, it was major and minor axis. For hyperbola, we have what is called the transverse axis, and we have the conjugate axes. The transverse axis is what is going to get us from the center to the point of our vertices on the hyperbola. So the transverse axis, look at the square root of what is positive and multiply it. So square root of a squared, which is a, and then multiply it by 2. So we're going to go to the left and right a to get these vertices if our hyperbola shape is going towards the x-axis. Where over here, the b value, b squared is underneath the positive. So we're either going to go up b or down b. So let's look at the formula there. So if it's with the x-axis from our center, we're either going to add or subtract a to get to these points. It's affecting my x value of my center. So it's going to be h plus or minus a comma k. Where over here, we're either adding b or subtracting b from the y value of our center. So our transverse axis, h comma k plus or minus b, is going to give us the points of our vertices of our transverse axis. The other point, which is actually not on the hyperbola itself, but it's going to tell us pretty much how wide is that parabola shape opening up, or how skinny is this conjugate axis. So technically, to get points on the conjugate axis, in this case, we're either going to go up or down b units. So looking at this number that is with a negative over here, I would go up b units or down b units. Technically, notice that these both have, you can see these slant or oblique asymptotes in here. Finding this point on the conjugate axis, this is going to help us build this box. So basically, we're going to make this box or rectangle. And basically, through the corners of our rectangle, on the diagonal, if I went through that, that is going to make my asymptotes. So if I went over in this case, I'm going to go over a units to the left and over a units to the right from my center. If I formed a rectangle with these points, and I went through the diagonal, so I'm going to go through the corners and I'm going to intersect the center. That again is going to give me these asymptotes. That's going to help me determine how skinny and wide is this hyperbola shape. Foci for the hyperbola, they are not, again, they're not on the perimeter of the graph. The parabola shapes are facing towards our foci. So we're going to have two focus. And it's always, so it would be if I drew that line, continued on with my transverse axis, the points would be here. And I'm going to either add or subtract C from my center to get these foci. In this case, though, foci are found a little differently. So my foci, so for the one on the left, I'm going to either add or subtract C from H, so H plus or minus C, comma K. Or my foci over here, I'm going to add or subtract C from my Y value, so H, comma K plus or minus C. I don't have the formulas memorized for my asymptotes, but notice it's an equation of a line, and we know how to find equations of a line. And if you don't, then you should, and you need to learn it. You have 2 points, right? We have more than 2 points that we can use. And if we have 2 points, we can find an equation of a line by finding the slope and the slope-intercept form. If you'd like to put that, though, on your formula sheet, Use the values of A, B to create the rectangle box. Around the center of the hyperbola, the diagonals of this box forms the asymptote, and the equations of the asymptotes are in the form y minus k equals plus or minus b divided by a all over x minus h. Again, I don't have that memorized. Usually, I will just have you graph those asymptotes just to help you. You should be able to find them, but I probably won't ask you to find it. Although that could be a good final exam question because it shows me how to find the equation line too. But let's go through and let's just look at a simple example where it's already in standard form and then go and graph this hyperbola. And then we'll go where it's not in standard form and put it in standard form and graph it. Okay, so we're given an equation of a hyperbola, and we want to find where the center of the hyperbola is, where the vertices of our hyperbola are, the vertices of conjugate transverse axes. Let's draw our ellipses and not ellipses, our asymptotes, and then draw our graph of our hyperbola. So looking at this, I noticed that y plus v quantity squared over 4, that's the positive piece. Positive piece is with a y, so this tells me that the shape is going to be going up and down. It's in the form where I can figure out what the center is. Center is always HK. H is always with the x value. So my center here is at 2, -3. My b value, b squared is 4. B is always the one underneath the y. So b is 2. My a squared, a is the one underneath the x. So a squared is 9, a is 3. So let's plot our center. So 2, -3. So over to the right 2, down 3. So I know that I want to get the vertices of that transverse axis. I'm going to use B because that's with a Y. I'm going to go up 2 and I'm going to go down 2 from the center. So if I go up 2 from the center, this is now at a point at 2, -1. And if I go down 2 from the center, I'm at -5 or 2, -5. Okay. So these are vertices of the transverse axis. The other one is the vertices of the conjugate axis. That's what it's called, right? So I'm going to go to the left and right 3 units. So if I go to the left 3 units from 2, I'm at the point -1, -3. And if I go to the right 3 units, I'm at 5, -3. Okay, so I want to form a rectangle with this. So let's form a rectangle. So I'm going to go up to the height of this point. I'm going to go all the way to the right till I hit this point. Doesn't look like a rectangle to me, but it is. And I get something that looks like this. And so I know that my asymptotes are going through this diagonal. And that's a line, straight line. It's going through these diagonal. this kind of tells me how wide is this parabola shape getting. And so I can plot it from, this is the vertices on my transverse axis. This is where like the vertex of that parabola shape is changing. And so we'll be hugging these lines. Conjugate axis, and then hug the lines. So really the graph is only these parabola shapes bouncing off of each other, kind of. The others are just there to kind of help us get a picture of what the graph is going to look like. We can get a little more accurate by finding our intercepts. We're pretty much running out of time, and I want to go through some more examples, so I'm not going to do that. But remember, and would be a great place to solve different types of equations, to find our x-intercept, let y equals 0, solve for x, find our y-intercepts, let x equals 0, and solve for y. So let's look at another example where it's not quite in standard form and we have to put it in that form. So we have an equation in front of us, 4x squared minus y squared minus 24x minus 4y plus 16 equals 0. Without being in this section, you should be able to recognize that this is a hyperbola. So remember, look at the coefficients in front of our squared terms. So our 4 in front of the x squared term and our -1 in front of the y squared term. These are opposite signs. This tells me we have a hyperbola. We want to put it in that form, and that we have that perfect square of our x terms, the perfect square of our y terms equals 1. Let's group our x terms together. Let's group our y terms together and get the constant on the other side. So doing so, I have 4x squared minus 24x minus y squared minus 4y equals, moving the 16 over, we're subtracting it on both sides of our equation, so it's equal to -16. Neither my x terms or y terms are ready to complete the square because those coefficients in front are not +1. So let's make it that way by just factoring the 4 out of the x terms. So if I pull the 4 out of the x terms, I would be left with x squared minus 6x. I'm going to want to add something in here to make that a perfect square. For now, actually, let's go over here, and then we'll talk about what we're going to do to the other side to make it equivalent. Over here, we need to factor the -1 out of our y terms. So if I pull a -1 out of the y terms, I'm left with y squared plus 2y. And I'm going to add something in here also to make this a perfect square. Equals -16 plus. So technically, whatever I did on this side has this 4 times what I added. So I'm going to have 4 times what I added over here. And the other one, technically distributing this negative to each term, I have a -1 times whatever I added here. Okay, so let's figure out what we're adding to make those a perfect square. So we half our middle term of -6 in this case. So -6 divided by 2 is -3. So the same number we added to get -6. Yes. Go back up here really quickly. over here, when I pulled out a -1, I don't know why I put 2, but this should have been a positive 4y. Wait, yeah, positive 4y. Thank you. So half of -6 is -3. I'm sorry, yeah, and -3 squared is 9. So I'm going to add 9 to make that a perfect square. Technically, it's 9 times this 4 that I'm adding on the other side to be equivalent of really what I'm adding to both sides of the equation. And this one over here, I'm taking my 4, divide it by 2 is 2, and 2 squared is 4. So I'm really subtracting off minus this 4. Okay, so let's rewrite this. This is 4 all times. This is now a perfect square. X minus 3 quantity squared minus, this is now a perfect square, y plus 2 quantity squared is equal to, so here I have, let's just do this on the side, -16 plus 36 minus 4. Combining my negatives, -16 minus 4 is -20. 36 minus 20 is 16. So I'm not quite in that standard form yet because it has to be set equal to 1. And that coefficient in front of the squares in the numerator has to be 1. So let's divide every single term on each side of the equation by 16. So notice that makes that 4. That goes into 16 4 times. And so I now have my equation in standard form and I can start reading things off. So I have x minus 3 quantity squared all over 4 minus y plus 2 quantity squared all over 16 equals 1. So from here, we can tell what the center is. Opposite sign, h is 3 and k would be -2. Looking at which grouping is positive, it's positive is with my x's. So I know my parabola shapes of my hyperbolas is going to be facing towards the positive and negative x-axis. Okay, so let's start graphing that. So 3, -2. So over to the right 3 and down 2. So my transverse axis, my value here, I'm going to look at 2a. A is equal to 2. So I'm going to go to the left and right 2 units from my center. So that's going to be at 1, -2, and 5, -2. So to form my box, this tells me I'm going to go up 4 and down 4 for my center. So from a y value of -2 going up 4, my y value now would be 2. And if I went down 4, my y value here would be -6. So we have 3, -6, and we have the point 3, 2. So from here, we're going to form our rectangle, make a box with these points. So you're going to get to the height and width by these points. We can draw our asymptotes by going through that diagonal in the center. Again, I know which way it's going, so looking at the vertices of my transverse axes. Going to be looking like this. And if we wanted to find the foci, let's just do that really quick because we didn't do that on the last one. We know that C is equal to A squared plus B squared when we're dealing with a hyperbola. So C is equal to the square root of 4 plus 16. So C is equal to the square root of 20, which is 4 times 5. Square root of 4 is 2 root 5. So for our foci, we are going to the left and right 2 root 5. It's always going towards the foci. So my H value, which is 3 plus or minus 2 root 5, and my Y value is going to stay the same of -2. So given an equation not in standard form, we were able to put it into standard form and graph it.